So exam 2 has been graded and mean is 26. Okay. And remember, exam 3 will be out on the exact date is March 17th. Okay, so we'll have the same thing, 48 hours, and it will cover topics from the last 5 lectures. Okay, so lectures 13 to 17. Okay, and 48 hours. That's before. Any questions about the exam? All right. So let's recap what we were doing last time. We were trying to give a space optimal or more space efficient algorithm for the tree eval function, right? So you had h comma k, which takes let's see. All right. And implicit in this description is that, maybe you can also assume the gate, the function f, right, is also given as some kind of table. Okay, so you can put this also in the input. The algorithm can handle that. But it's interesting even if somehow you're allowed some pre-processing with f. Okay. All right. And the rough idea we had was to use this offsetting operation and kind of save on reusing the registers, right? So recall our overall approach was to have these 3 groups of registers. Okay. And this was something like RA1 up to RAK, RB1. And the intuitive idea is to implement the following primitive. So you want to implement offset of a node u, right? So that means you're trying to compute the function at that node, depending on the inputs and the height of the node. And so let's say if I give it, this is RA bar, the vector. So I want to implement this function. I call offset u, RA bar, RB bar, RC bar assign. And then we want only the third register to change. So the result should be that this gets offset by the value of the function at the node. Okay, this is our goal. This is a definition, and we want to do this without changing the registers RA bar and RB bar. And we also want to do this by register program. Right? Register program meant you always had instructions of the form, okay, assign RA to something, one particular register to something based on 2 other registers. Okay. That's for simplicity. It's just as powerful and it's cleaner, so that's what we're going to do. Okay. All right. And the idea was to use induction and some other stuff. All right. So let's recap. We had this claim, so let me now prove that claim. One of the claims that we had was we wanted to extend the domain of the function, right? The function f is only defined on bits, but we are going to compute something more powerful, which will allow us to do better recursion, essentially, right? This also happens in inductive proofs, where you sometimes strengthen this statement that you're trying to prove So that helps you with induction. Okay, and the same thing here. We are going to compute something more powerful so that it will help us in the recursion, right? And I said it last time, but now I want to give an explicit expression for this multilinear extension so that it's also clear that you can compute it, right? If I'm giving you this function as a table, I also want to be able to compute the multilinear extension in small space. Okay. So how do I do that? And so recall what's the claim? We are given this function f. So there exists a degree less than or equal to 2k polynomial. Okay, so we're going to pick some finite field. You can think of real too, but finite field is helpful because we want to start cutting off things and we really want to save on space. So it's a finite field and it's a degree at most 2k polynomial. In fact, it's going to be multilinear, meaning it's a polynomial where each individual variable has degree at most 1. Okay. So for example, something like y1 z1 plus y2 z10 and so on. Okay. And you can have coefficients coming from the finite field f. And to do this, we need, well, we can do this as long as anything is true. So how do I do this? I mean, the point is that we only need to satisfy these equalities over 0, 1 through the k. Okay. So we can encode it explicitly. So proof, and this is also, you can think of it as an algorithm. I'm first going to write down a seemingly weird expression, and then hopefully you'll be fine with it. Okay, what did I write down here, right? I'm saying I can express f tilde. I'm just defining some function in this way. Hold on 1 second. I think I need to change this a little. So the idea is, I'm going to somehow explicitly enumerate over these things, right? And then you'll have, let's see. Maybe let me just simplify this actually. Okay, so imagine I define a new function, f tilde I, as follows. It checks if y equals alpha and z equals beta, and then for every such alpha and beta which are in this 0, 1 to the k, it just computes f alpha beta and outputs I. Okay. So what does it do? In suggestions, what is it doing there? What does it compute? What happens when I give it some other value? If I give it, sorry, say that again. If it's not in 0, 1 to the k, it will give 0. And in 0, 1 to the k, it will give you the actual value. Okay? So this is one way to do it. The only downside of this is that this expression is not really multilinear. I cannot encode it as nicely as a polynomial. Okay? So this is the first thing you might try. Like, let me just expand it out in this sort of brute forcey way. But yeah, so it doesn't quite work. So you have to just slightly change it, and you can do that. So the expression becomes a little bit more messier. In particular, well, actually, I think we are going to run out of time if we do this. But okay, so let me just say this is the rough idea. This is already looking like a polynomial. Okay. The only thing is that we have this indicator function y equals alpha, which we have to encode as a polynomial. And you can then massage this a little bit to get this final expression. Okay. This is just to give you an intuition for how the proof is going to go. The exact expression is a bit messy, but it also tells you that if I have such an expression, then I can compute it in small space. Why? Because it's just a giant sum of things. And I just enumerate over the things and then keep computing the sum. Okay. And the sum is small space because it's a finite field, right? So you're going to always wrap around. Okay. So this is always an element of F. So can be computed with space roughly log. Okay. As long as a giant sum, space is very good. Space can handle for loops very easily, especially if it's just addition. All right. Okay. And this is kind of the standard way to multilinearize stuff. You just take something over 0, 1 to the k, compute a polynomial, and then just take the variables to be your finite fields. That's what you do. Okay. All right. So that's one. Next, what do we do? Is this clear, or do you want me to elaborate on it? Any questions? I see a lot of puzzled faces. Okay, so let me just maybe write down one more equation. So for example, I can write this as, let me take it one step at a time. I can write the real function f in this way, right? And I can expand this as some polynomial. Okay, imagine if y is only over 0 or 1, then I can easily write it as a polynomial. I'll just say something like, let's see, what do I want? If alpha I is 0, I need to check if yi equals that, right? So maybe it's like computing the AND. So what is this saying? If alpha I is 1, this is just putting y1, right? So if y1 equals alpha 1, you know, imagining that the inputs are 0, 1 to the k, you would get exactly 1 here. Okay? And the same thing here. This should be beta. So this is the indicator of y equals alpha, indicator of z equals beta. Okay? But this only works when y and z are 0, 1 through the k. Only if it's 0, 1 through the k. We are going to use the same expression and oh, wait. What did I do here? That's true. Did I do any mistake? So if alpha I is 0, oh yeah, this should be 1 minus yi here. Thank you. Right, perfect. This is what we want. Right? So if, so this, this is essentially only non-zero when alpha I equals y, right? If alpha I is 1, yi should be 1. If alpha is 0, yi should be 0. Okay? But over the hypercube. So this expression is only true when y comma z belong to 0, 1 to the k. All right? But we are going to ignore that these are values over 0, 1 to the k and just plug in the finite field values. Okay, so that's the multilinear extension. So this times, okay? So now my f tilde I of y comma z is just going to be this polynomial. What does it compute? It could potentially compute something weird over the finite field. But when you put in the 0, 1 values, it will exactly match what we want. Okay? So this is our f tilde I, which is a polynomial, and its degree is at most 2k because each one of these terms is a product of 2k things, which are linear. It's multilinear because each variable has degree at most 1. Okay? And you can compute it efficiently in space just by putting a giant sum. All right? Okay. So that's the multilinear extension part. And as I said, we were going to use it. That's the first thing that we took for granted in the last lecture. Now we have that. The next thing was about polynomial interpolation, but we'll get there slowly. Okay? All right. So the second thing that we took for granted was we said, okay, P is a univariate polynomial of degree less than or equal to 2k. Okay. Then I can write P of 0 as okay, this was the claim. And the point is that the coefficients C alpha do not depend on P. They only depend on 0 and the set of interpolation points. Okay. Why is this true? You can prove it in various ways. One way to prove it, in fact, is to just compute these things explicitly. There's a closed form expression for that. It's called Lagrangian interpolation formula, but we don't need that. Instead, as I said, we're going to pick a specific set of interpolation points to make the computation even easier. Okay? So in this expression and the idea from last lecture, we still needed to compute this coefficient CL. Okay? And they could potentially be a little bit messy. Right? So how do you get around? So the way to get around that is to use some thing standard from finite fields, but also very clever if you're seeing it for the first time, right? So, and what is that? And comes down to the following. Okay, so we have a finite field F, and let's say size of the finite field is m plus 1, okay? Meaning the multiplicative group, which does not include 0, F slash 0, that has size m, okay? And if omega is a mth primitive root of unity, okay? It's kind of a mouthful. But what it means is that omega to the m equals 1. It's an element of the field such that omega to the m equals 1, and omega to the I is not equal to 1 for all I, which is less than. Okay, it's the least index where it equals. Then okay. So then you have this expression that if I add up all of the powers, you get 0. Okay. And more generally, this is also true. So if omega is an mth root of unity, and so is any other power, like omega squared is also an mth root of unity, omega cubed is also an mth root of unity, and if it's a primitive root of unity, they're all primitive roots of unity. Okay? So in particular, you have this identity. All right? Okay. How do you prove it? The various proofs, but as I said, it's kind of standard in finite fields or algebra. This is the only fact that we need, okay? And once we have this, there is this, again, remarkably simple property. Okay. I take any polynomial whose degree is less than the field, finite field. We need that just so we have some, we don't have wraparound issues. Then P of 0 is okay. So what this is saying is I can interpolate, figure out the value of P of 0 from the value of the polynomial at all of these other. Okay. And the way to interpolate it is also very easy. You just have to add them. Right? So it's the same thing as the C alpha identity, except that here the coefficients are just 1. So you don't have to compute them. You already know them. Right? Any questions about this? And how do we prove this? You say, okay, I can take my polynomial to be something like this. Maybe it has degree d. I have ci times x to the I. I get p of 0 is c0, right? And if I add up I can interchange the summation. I get okay. So I just interchange the summation, and now we can use this identity. So we know this sum is 0 unless this exponent is a 0. So this just becomes m times c0. Okay. So we have this simple identity, and that's where the algebra ends. We really need this identity that I can figure out the value of p of 0 from all of the other values in a very simple way. All right. So now going back to what we were doing, so let me write down the algorithm, and then we will analyze it. So what happened? Okay. So 3. So how do we do that? And we said we are trying to compute the offset value. So we have a node U. We have this registers RA bar, RB bar, RC bar, and some sign. I'm going to write it when the sign is 1. When the sign is -1, you just have to change some things appropriately, right? Okay. So we're going to do the following. For I equals 1 through so this is basically the interpolation part. Maybe let me use index j here, right? And we'll also compute each bit of the RC separately, right? So we're going to compute RC1 separately, and then RC2, and so on. So how do we do this? The first step is to say set RA bar to be alpha times omega. I'm updating the contents of the registers to scale them up. And this is like our alpha. And then we say offset u dot left So notice that the answer is now being stored in A, right? So these things have changed. The ordering has changed. This is the same trick that we used in Benner and Cleave simulation, right? So the in the final step, we want the answer to be stored in the third register, but for the left node, we store the answer in the first register. But the offset property is that it doesn't change what we computed in the other two. Okay, and then we do u dot write of right, so this ordering is changing. And what's the status after this? Or the state is going to have, we have 3 registers. And if you think of it as a vector, this is going to have whatever you started out with plus fu dot left. And this is going to have whatever you started out with plus u dot right. Okay. And we said we'll view this as y, this as z. The next thing we'll do is for I equals 1 through k. So now we are updating every one of these individual registers in the third group by using the polynomial. Right? So whatever is stored in the current register, which is these two values, just evaluate it here. Maybe, let me also do it right here so that it becomes clearer. Plus m inverse times. So m inverse is like the C alpha that we have, right? We're just adding up all of them with this. Okay. So after doing this, I want to reset it, right? So I multiplied with j. When I go to 2, I don't want to again do the multiplication, right? I want to reset it so that I undo these updates and get it back to the original RA bar and RAB bar here. Okay. So this is the cleanup part. Right? So when I say minus this sign, it's going to decrement RA bar by fu dot left, so that y will be removed. And the same thing for the z. And then we have to divide by whatever we did. So we say this. Yeah. F tilde I is basically computed using this formula. Right? That's why I wrote down this formula, because that's like another subroutine, right, that you have to use. We are assuming that we have access to f as a table. Like, if I tell you y and z, some whatever values, it'll tell me what the value is, right? So now I have to This is kind of a separate subroutine which always computes this. That's like additional space. Takes additional space, but it's only the field size. Okay, so it's small. Use what? Sorry. No, no. This is just like a big for loop for us. Yeah, I mean that's a good idea. We potentially could have, but we don't need to because it's just a big formula, and it's a simple enough thing that we can do it. Okay. Yeah. So maybe let me add that remark here. So computed using form. Right. So in the end, it's a simple enough pseudocode. You can code it up presumably as long as you can support finite fields easily. Right. It's just like 4 recursive calls, and then you have this other stuff. So it's very similar to the Benor and Cleve thing in terms of the structure. All right. And the correctness in the end, so the claim is in the end, we actually have RA bar is the same, RB bar is the same, RC bar is exactly what we want. Okay. And how do you prove it? You prove it by induction. Okay. I guess I missed the base case of the induction, which is if U is a leaf, you just set RC to be plus U dot. Okay, that's the base case of the induction. All right. Okay, any questions? All right, so let me stop with that. And what else do I want to say here? You have to be when you're implementing it properly and or doing the space accounting properly, you need to make sure that the finite field computations can also be done in the space that you expect them to be done. But all of those are standard in algebra. You have all computational algorithms for kind of working over finite fields of any size. You have to pick an appropriate irreducible polynomial and so on. But that's sort of black box access for us. Okay. Okay. So maybe let me just say a few words about the proof. At the end, what we have is going to be, because of the for loop, for each index I, what I am really computing is f tilde I of okay, so by induction, let's say the left and right nodes are computing the proper thing. Then if you just unroll the for loop for each register, I'm just adding up these things exactly, right? And the state we said is this, right? And there is an M inverse here, so let me put that in. Okay. And I can define a polynomial P of, let's say, X is, maybe let me not use X, let's say, beta is Okay. So this is a, f tilde I is a multivariate polynomial, but y and z are fixed, and so are Ra and Rb bar. The only thing that's changing is this omega to the j. Okay. So I can view it as like a univariate polynomial. The only parameter really is beta, which I'm plugging in. Okay. And now we have all the tools that we earlier discussed. Degree of P is less than or equal to 2k, right? F tilde I was a multilinear polynomial. It had total degree 2k. So if I just substitute beta in each one, the degree of this in terms of beta will also be 2, right? And this implies that P of 0 equals M inverse this was the roots of unity identity that we had. And this implies that okay, which is what we want, right? And this is just fu. Sorry, this is just f of y comma z. Because y and z are elements in 0, 1, 3. Okay. All right. So that's basically it. And what do we gain from this? Just to summarize, we covered most of the details. You just have to be a little bit careful in how you do the summation and do some careful accounting for how the whole space goes along. You need to make sure that even the for loop indices can be stored appropriately. How many instructions you go, that also you need to store. But there's some, slightly non-trivial, but still mechanical bookkeeping. Okay. The summary will be that the tree eval problem with height h and gates of size k can be computed in space O of h plus k times log. Okay. And this additional log k comes in because we need the field to be bigger than the degree that you're dealing with. The degree is 2k. The field has to be bigger than 2k. That means your operations will be log of the field size, right? It's a very surprising result, but in the end, it's just 10 lines of code, which is here. And it's using polynomials very strongly, right? Somehow this magical property is playing a very important role. Where is that? Yeah, this one. Okay. Yeah. Right. So the large enough field only because we need the size of the field to be higher than the degree of the polynomial. Okay. So the degree is 2k, so we need the field to be bigger than that. Or in other words, for interpolation to happen, you need for interpolation, the number of evaluations must be more than the degree of the polynomial. Okay. So think of a polynomial as, like let's say, okay, so just imagine I'm in 2 points and I have someone tells you, okay, there is some linear function and I want to know what is its value at 0, but I can only tell you its value at 1. If I just know this, I cannot know what the value at 0 is, right? But if I give you one more point, if I tell you its value at 2, then I know its value at 0 if it's a linear function, right? Because I would just draw the straight line and, well, that's not a straight line. So I would draw a straight line like this. And now the value at 0 is fixed, okay? And similarly, if you have degree 2, then I need the value at 3 points, right? So I have, maybe here and say here. If it's degree 2, it's like a parabola, then I don't know its value at 0. It can be anywhere. But if I give you one more point, then I know its value. If you tell me something like this, then I can fit a parabola and know exactly its value here. Right? So to know the value at 0 from other points, to interpolate it, if the degree is d, I do need its value at d plus 1. Okay? That's what we are exploiting. All right. So that's all I wanted to say about tree evaluation. And as I said, it was pretty surprising because people did think for a while that it does require a lot of space. And I also said that it was most recently used by Ran Williams to show that you can actually get amazing savings for general computation. It's not just for the specific toy or seemingly toy-like problem. You can actually get savings for any multi-tape Turing machine. Okay. If we had maybe one more lecture, we could have covered that. But unfortunately, we cannot, there's not enough time to do it. But it's really clever and very, very surprising. Okay. At least to me. All right. So in the remaining time, I want to give another example of the polynomial method. And this is it's kind of a proof from the book, whatever that means. It's like a very clean and elegant proof for a problem that had been open for a long time. And this is called the finite field. Okay, problem. Okay, so let me first find one video. Okay. Okay, so a Kakeya set is a set which contains a line of unit length in any direction, and it has to be continuous. Okay, so meaning it's a set where just imagine there's a needle of unit length, and I have to rotate it along all directions while being completely in the set. Obviously, I can do it in a circle, just spin it around in a circle, and that's fine. But the weird thing, and surprising at least until you sit down and draw some pictures and see some animation like this, is that you can do it while covering very little area. Right? If I do it in a circle, I have an area pi over 4. So here, it's much smaller than the circle. Right? And if you can see it, like, it's going around, it's rotating fully, but always staying within this set, black set, in a continuous way. And the area that it's sweeping is very small. Right? In fact, there are sets where the area is actually 0. But then you can talk about other kinds of dimension or other kinds of areas and then make it interesting. Okay? And the finite field version is kind of the same. meaning the following. So a subset of, Fn or n-dimensional FSM field is a Kakeya set if for every direction that you pick in f to the n, for every x, there exists a y such that okay. So what does this mean? It means that if I draw a line along the direction x, then there is some translate of it. I allow you to pick the translate. There is some translate of it which makes me completely contained within the set S. Okay. It should, I mean, does the definition at least make sense? So I'm saying for every x, all of these, if I pick this direction, for example, it's a vector, then along that vector, I need to find these, the points where the t is changing, right? So maybe this is y plus x, y plus 2x, y plus 3x, and so on. All of these should be in the set S. Okay. It's kind of the same thing over the real space, right? We said you pick a direction and I need to see this line segment in that direction in my set, the needle. Right? It's kind of the discrete version of the needle. Okay. So the Kakeya set problem, which was originally coined over the real numbers, but then the progress they were stuck. So people started looking at the finite field version. And here, the notion of volume becomes the size of the set. Okay, so the question is how small can a Kakeya set be? Okay. Of course, I can take the entire space, then it is a Kakeya set in that it contains the line in every direction, it contains every point, but that set is very big. How much smaller can I be while having this property? Right? So the real numbers we said, I can get a set of zero area which contains a line in every direction, which is counterintuitive, but that's true. Okay? How small can it be over finite fields? Right? And basically until this was studied for several years, and people only had something like, okay, it should have at least n elements or 4n over 7 elements or something, which was painful to prove. Okay? But then in 2008, Dwyer showed that the Kakeya set must have size I'm looking up the exact bound is let me state it this way. Okay, so the point is that as a field grows, this is getting bigger and bigger, whereas this bound did not depend on the size of the field at all. Okay, The Q is the size of the field. This should be S. Every Kaka set S must have size at least something. And now we kind of know the exact asymptotically optimal constructions and uh, lower bound as well. Okay. In particular, you can get like exponential size as long as Q is slightly big enough. So how do we prove such a thing? And the proof is quite magical. So it relies on encoding this property of Kaka sets as a polynomial. Right? This is the polynomial method we've been talking about. We encode some interesting property in terms of some polynomials and then get some contradiction or use it in some way. That's what we saw in the 3AP problem, the CAPSET problem, right? So we proved the slice rank property using polynomials. In the last tree evaluation problem, polynomials played a role in that they have this very clean interpolation form. Okay. The last thing we are going to see is this sort of, it's kind of maybe using interpolation too, but also some kind of root counting. Okay. So to prove it, we need two properties of polynomials. The first one is what's called Schwartz-Zippel lemma. Okay. And I'm only going to state the simple version that suffices for what we are going to need. There is definitely a more quantitatively better version. Okay. All right. So what's the Schwartz-Zippel lemma? So remember that if I give you a polynomial p over some field of degree d, how many roots can the polynomial have? So number of roots of p is less than or equal to d. Okay. If I have a polynomial over the real numbers, the number of roots it can have is at most d. Sometimes it might have less roots depending on the field that you're working. If I give you a multivariate polynomial, what can you say? It's not clear. Or the real numbers, now you cannot say the number of roots is finite even. If I take the polynomial like x minus y whole squared, it's two-variate, it has infinite number of roots. Okay. Over finite fields, you can still count. Even over real numbers, you can count, but let's not get into that. Count in a weird way. But over finite fields at least, can you count how many roots can you have if it's a multivariate polynomial? Okay. And it turns out you can still get meaningful bumps. Meaning, suppose I have a multivariate polynomial now, something like this. And then the number of points where f is actually 0 is at most the degree of f times q to the n. Okay. So it's definitely less than q to the n as long as the degree is small. Q to the n is the total number of points. We're saying if the degree is small, well, you cannot have all the roots, all the points as roots. Okay. But you can actually get even stronger versions depending on the things, but this is easy to prove and this is enough for us, really. Okay. All right. So that's in property number 1. The next property is the following. Okay. So over the real numbers, let's say I tell you, okay, here are, my set of points. I give you a set of points and I say, give me a polynomial which is 0 on all of these points. Can you do it? Yeah. I mean, if it's, let's say this is 1, this is 10, this is 17, this is 21, 25. I can define a polynomial which is 0 at all of these points. Okay, so this is a polynomial which vanishes at these points. So in general, if I give a set of d points, I can construct a polynomial of degree d which vanishes at all of those points, right? And there is an analog of it in higher dimensions. But when you go to higher dimensions, you start gaining a lot. Okay. In particular, so suppose I have a set S subset of fq to the n. This is a finite field of size q. So remember, our size of the field is q. Okay. And if yeah, as long as the set is smaller than this, there exists a degree less than or equal to d polynomial that vanishes on S. Okay. So imagine n equals 1. So what is this saying? As long as the size of the set is less than d plus 1 choose 1, which is d basically, right? D plus 1. So a size of S is less than or equal to d. I can find a polynomial of degree at most d that vanishes on S. Right? That's what we saw here. This is kind of the higher dimensional version of it. In higher dimensions, like in F2, it's saying I can find a degree d polynomial which vanishes on any set of points. There's no structure required on this. On any set of points, as long as the number of points is at most d plus 1 choose 2. 3 dimensions is d plus 2 choose 3 and so on. The exact constants are not that important, but basically it's like d to the n. That as long as the size of the set is smaller than like d to the n, I can find a polynomial of degree d which vanishes. Right? Okay. So these two claims are basically enough to prove the finite field Kakeya-Hassett conjecture. All right? Okay. So let me just say example. If d equals, if n equals 1, any set S, size of S is less than d plus 1, there exists a degree less than or equal to d polynomial. Okay, which is straightforward. It's just like this. The other cases are more interesting. Okay, it's not easy to kind of directly guess what this polynomial is going to be. You have to do some dimension counting and so on to actually find this. Okay, all right. So how can we use this? Now let's go back to the Kakeya-Hassett problem. suppose, actually, we can state the exact theorem first, maybe. S is a Kakeya set implies size of S is greater than or equal to Q plus n minus 1, choose n. Okay, so it's an n-dimensional set over a field of size Q, and it's a Kakeya set. We want to say it implies that the size of the set is at least Q minus 1 plus n, choose n. Okay. So the proof is kind of almost, you can start guessing how it's going to go given these two expressions. Okay. All right, so let me see you guess. The proof is going to be a contradiction. Suppose there is a Kakeya set S of size okay, suppose this is true, that there is a Kakeya set, something like this. This implies by claim 2 that there exists a non-zero polynomial P of degree less than or equal to Q minus 1, right? So I'm just applying with degree D being Q minus 1. Such that P of x equals 0 for all x in the set. Okay, so I can find a polynomial which vanishes at every point in my set S. It might vanish at other points too, but at least it vanishes at every point in my set S. Okay, so far so good. But we haven't used any property of the Kakeya set so far. We just said, okay, something like this, right? And now let's understand what this means, right? So it's saying on the other hand, maybe let me use slightly different notation here. On the other hand, we also know that for every x in my space, there exists a y such that x plus ty belongs to S. Right? So this is the line property. Pick any direction. I need to find the entire line contained in my set S up to some translation. Right? So this implies P of x plus ty equals 0 for all t in my field. Okay. And the punchline basically now is that, okay, this is a univariate polynomial. I can think of it as a univariate polynomial in T. Okay. So define Q of T is P of x plus Ty. Now what do we have? We know Q of T equal, maybe not Q, let me use, say, R. How big is the degree of R as a polynomial? So remember, if I have a multivariate polynomial and I plug in, like I make it univariate in this way, the degree does not grow, right? So its degree is at most q minus 1, right? Because we have this here. Okay. So I have a polynomial whose degree is q minus 1, but it is 0 at every point in the field. So meaning it has q zeros. The only way it can happen is if this polynomial is basically 0. Okay. And so that's basically the point. So this implies R is identically equal to 0. Okay. And let's see, how can that happen, right? So we have this polynomial. Maybe let me put Rx of t here because it depends on x. So I have Rx of t equals p of y plus dx is identically 0. Okay. Meaning every coefficient of t, when you expand it out, must be 0. Right? It's identically 0. There are no non-zero coefficients if I view it as a polynomial in t. What is the leading coefficient of this polynomial? Any guesses? What's the highest coefficient of this polynomial going to be? Well, it depends on the structure of P, right? So claim, maybe not claim, but let me just say, let's write down P as so I have this polynomial P, and I can split it up into, okay, just a constant term, all the things which only involve degree 1, like z1 plus z2 plus zn, all the things which only involve degree 2, z1, z2 plus z2, z3, and so on, and the highest degree terms. Okay, I'm separating out based on the degree. The reason I'm doing that is when I when I substitute this y plus tx, the different terms can intermingle, but the leading term will never get disturbed. Okay, so if I write Rx of t, which is p of y plus dx, it's going to be some stuff that we don't really care, but the highest coefficient is just going to be this. Okay. So just as an example, imagine the polynomial p had degree 2, right? Then I'm saying the quadratic term where t square appears is only whatever was degree 2 in the original p. The linear terms won't interfere with the quadratic terms. The quadratic terms might interfere with the lower things, but the linear things won't interfere with the quadratic things. And the same thing here. Okay. So this implies that, so what should this imply? Well, our polynomial R itself is identically 0, right? So all of its coefficients are 0. In particular, the leading coefficient must be 0. Okay. Right. So we get this multivariate polynomial, which is of degree d less than or equal to q minus 1, and it is 0 for all x. Right. So why is this, what can we conclude from here? Any deductions or any claims that we can use now? So I have a multivariate polynomial. It's of degree d, where d is less than or equal to q minus 1, and it is 0 at every point in fq to the n. Is this possible or not? Right? So this is 0 for every point in fq to the n. Okay? So what can we use to contradict it? Yeah, okay. All right, so we can use the Schwarz-Zippel lemma to say, yeah, so this is a contradiction to contradiction. Right? Because PD is of degree less than or equal to q minus 1 and is 0 everywhere. Okay. So we are peeling off one term at a time, right? So we said, so this must be 0, and then this must be 0, and this must be 0, this must be 0. Eventually, you'll get this polynomial itself must be. Okay. So we keep repeating this. So by repeating this argument, we get that the polynomial p, the special polynomial that we constructed, is 0, which is a contradiction. Okay. Right. So because we said, by claim 2, there exists a non-zero polynomial such that it's of degree q minus 1 and vanishes on the set S. So we're gaining something from the fact that, it's a Kakeya set. The set S is small, so I can find a polynomial which is non-zero and vanishes that. But the set has a structure. Because of a special structure, not only can I conclude it is 0 in the set, but I can also conclude it must be 0 everywhere else in the space. Okay, so that's the sort of magical thing that's happening here. It's again related to interpolation. If I tell you the value of a polynomial on some set, I can use it to infer its value on many other places. And here we're inferring it weakly in the sense that if I tell you it's 0 in the set S and the set S has a Kakeya property, then I can infer that it must be identically 0 everywhere. Okay, which is a contradiction. All right. And yeah, so that's basically, so this implies that every Kakeya set has size leaves So before this simple polynomial method proof, people had very complicated additive combinatorics arguments based on many sum-set estimates and so on to show very weak bounds. Okay? And if this is roughly 1 over n factorial times q to the n. And but we now know that the right answer is something like yeah, we do know that the constant 1 over n factorial has also been improved to something like this. And this 1 over 2 to the n minus 1 is actually tight. People have constructed examples where there is a Kakeya set of size roughly q to the n over 2 to the n. Okay. And the proof of this improved lower bound is again by the polynomial method. You just have to use a more sophisticated form of Schwarz-Zippel lemma. Okay. All right. So let me stop with that and say what are the key things that we learned, right? So okay. Irrespective of the structure of the set S, as long as the size of the set is small, I can find a low degree polynomial which vanishes on this. Okay. Typically, if you're in n dimensions, this degree of the polynomial, you should think of it as basically the degree is something like n times size of S to the 1. Okay. So if you're in 1 dimension, it's basically saying I can find a polynomial whose degree is roughly the size of the set which vanishes on it. If you're in 2 dimensions, it's like square root. If it's in 3 dimensions, it's like cube root and so on. This fact surprisingly gets used a lot in error correcting codes. It forms the basis of Sudan's list decoding algorithm, which is really, really important algorithm in error correcting codes and in many places. The second thing that we used was Schwarz-Zippel lemma. Yeah, which is essentially multivariate or root counting for multivariate polynomials. Okay. So we know that if I have a degree d polynomial in one variable, it can have at most d roots. But if I have a polynomial in 2 variables, how many roots can it have? It can have more roots than the degree of the polynomial for sure, right? If I take the polynomial x minus y, it's degree 1, but it has many, many roots. You cannot just set x equals y, right? Even though it has many roots, the number of roots is small relative to the number of options, right? If it's x minus y, it has q roots, where q is the size of the field, but the number of options is q squared. Okay? And Schwarz-Zippel lemma gives us a way to kind of count this, account for how many roots can you have relative to the total number of possibilities. Does that make sense? And you can phrase it in terms of probability. And that forms an important part of many, many cryptographic tools, where you want to test if a polynomial is 0 or not. I can just evaluate it at a random point because the number of roots is going to be small. Okay? Should say this forms, exploited, used a lot in decoding algorithms and so on. And this is used for testing computation. Okay. So if I want to test if some polynomial has been computed correctly, then I just had to check it at some random points and I'll be fine. Okay, that comes from Schwarzschild. All right. Let me stop with that. And any questions about this or the earlier stuff that we discussed about tree evaluation? Okay. So if not, I don't want to start a new topic given the 10 minutes that we have. But if you're interested, you should check the new paper showing the time is in square root of space, more or less. It involves some additional tricks and a lot of cleverness in how to encode computation on a Turing machine to a tree evaluation problem. Okay, but we saw the tree evaluation problem. You have to kind of enhance it a little bit and then reduce the computation on Turing machines to that. Okay, but I think you can read it given what we already know. All right, so let me stop with that. And remember, the exam will be on 17th is a Monday. I think so. The exam will be on Monday. Okay, and I'll release it at 6 p.m. again. Yeah. Claim 2, this one is, so how do you prove such a thing? It depends on if you know linear algebra. Okay, so what do we need, right? So what is that claim saying? Again, if you think of bang per buck, the equivalent of bang per buck is the utility versus difficulty in proving. This is very high up there, okay? As I say, it's very, very important in error correcting codes and many other places, but it doesn't use any sophisticated algebra except dimension counting. Okay, what do I mean? So let's say I have a set of points, S is some, x1, x2, up to some x. Okay, I have some endpoints, and I want a polynomial of some degree to vanish on. Okay, and how do I write down polynomials, right? That's the first question let's ask, that we should ask. Well, polynomials are specified by the coefficients, right? So if I have a if it has univariate polynomial, then it has d coefficients, or d plus 1 if you count the constant. I have d plus 1 sort of free parameters to choose a polynomial of degree d. In the multivariate case, how many parameters do I have? Okay. So let's say, I could choose for degree d equals 2, it would be something like, let's say, have the constant term, okay? Then I can have something here, then I can have something here, then I can have z1, z2, but I can also have, let's say, maybe let me write these as 1, 0, 0, 1. Okay. This is what a degree 2 polynomial in 2 variables would look like. Right? I can have the constant term, the linear in z1 term, linear in z2 term, z1, z2, z1 squared, and z2 squared. Okay. The 0, 2 comma 0 is saying that, okay, the degree of 1, the first variable is 2, the degree of the second variable is 0. Okay. So in the same way, I can write down this polynomial, the representation as ci1 up to in, z1 to the power I1, z2 to the power I2, zn to the power in. The only constraint is that these powers must add up to at most d. Okay, I can put all zeros, I can put a single one, I can put d in one place and zeros everywhere, but they should not go above. That's the only thing. Okay. And what are the equations that I need to satisfy? I need to have p of x1 equals 0, p of x2 equals 0, and so on. Okay, I'm looking for a polynomial which satisfies these things. And obviously, a trivial solution is to set all c's to be 0, but we want a non-zero polynomial which satisfies these things. Okay. And the punchline really is that every one of these equations, it seems complicated, but it is simple in terms of the coefficients. Okay. Why is it simple in terms of the coefficients? In terms of the coefficients, it's a linear equation. Okay. So let's look at this guy. Means I can write it as just imagine I have this entire coefficient vector. It's summation C I1 through IN. I1 plus IN is less than or equal to D times something. Okay, which only depends on I1 through IN and X1. I'm just using some shorthand here. The monomial corresponding to I1 through IN evaluated at the point X1. Okay. Implies this equals 0. And I can write this in this sort of equation-like form. This is a C vector. I have each coordinate is indexed by this I1 through IN, where they add up to less than or equal to D. And then here I have M I1 through IN of X1. Okay. And I want this to be 0. Right? That's what the property P of X1 equals 0 means. So someone gave us these points X1 through Xn, and we're trying to find these coefficients. Right? And I can do this for every other point now. So I have X2, so on, up to Xn. Okay. So the number of rows here, the number of equations is capital N. What is the number of columns? The number of columns is the number of tuples of n numbers which add up to D, or less than or equal to D, which is exactly D plus n minus 1, choose n. Okay. Right. So at the end, what I ended up with is I have this giant sort of matrix system that I want to solve. 0, 0, 0. Okay. I have capital N rows and these many columns, and I want to say whether or not there is some solution C bar such that this times C bar equals 0 has a non-zero solution. Okay. And a fact from linear algebra is that as long as the number of variables is more than the number of equations, there exists a non-zero solution. Okay, that's the only thing from linear algebra that we need. That it's basically like the row column equals column rank. So if such a system, if you have the number of columns more, strictly more, there will be a solution. So that means as long as n is less than this, there is a non-zero solution. Okay, so that's the proof of claim 2, right? So you all you need is the row rank versus column rank thing. But it's amazingly useful. Schwarzschild you can prove by induction. It's not related to this at all. Okay. Any other questions? Okay. So hope you had, some of the topics were very interesting for you. And if you like to know more about them, I linked to some of the papers. And if you want even more follow-ups, you can even ask me anything. Okay? All right. So next week, the exam will be out on Gradescope. And good luck with it.